If you looked at our schedule today, what we have on tap is that we're supposed to review complex numbers today. But what I have found over the years of teaching is that if you don't tell someone why they're learning something, then it's much more difficult for them to learn it. So I thought I would, instead of just diving right into sort of the nitty-gritty of what you do with complex numbers, what I wanted to do is try to present the why, right? What is it that complex numbers have to do with electricity? In particular, what do they have to do with alternating current, right? We are starting today on a whole new set of topics, and they have to do with alternating current. This topic goes a lot further than we are going to go with it in this course. We are going to essentially focus in on AC current or AC voltage, right, or the AC analysis, where we only have one frequency that we are dealing with and where everything is at steady state, right? So we're going to kind of hone in our scope a little bit when we're dealing with our AC analysis, but there are other examples of analyses that can be done that are things like transient AC or things like multiple frequencies that are all coming together in a particular circuit. So we are going to focus in on sort of the beginning part of this, but the good news is that actually has a lot of application, because the power that gets delivered into your homes or even to this classroom or whatever fits in the category fairly neatly of being a single frequency that's coming in there, and we very seldom deal with things like transients when we're analyzing those kinds of things. So that's kind of a bigger question or bigger presentation of the scope. Let's look at what do complex numbers have to do with alternating current, okay? So just to get started, let's probably review something that you are all comfortable with, and that is it's called the rectangular notation for a complex number, okay? I wrote it up here as a plus bi, where I, and this I has a kind of a more official name to it than just I. Sometimes this is called an imaginary unit, okay? And what it represents is the concept of the square root of -1. Now, already I tend to lose people if I say we've got the square root of -1 going on, because the realists in the room say, you can't have that, all right? What I want to comfort you with is that if you kind of imagine what kinds of properties the square root of -1 might have, it turns out that there are some mathematical patterns that pop out of that are useful for what we are doing, okay? So kind of run with it, because what we're at the end of the day trying to use is some beneficial mathematical patterns that pop out of kind of the theory around complex numbers, okay? Now, you are familiar with, in this class, we typically use the letter I to talk about current. And so in electrical engineering, what is customary is that instead of using the letter I to denote the square root of -1, that is the imaginary unit, instead of doing that, we actually use the letter J. It's not different, it's just a different letter that we use so that we're not stepping on the letter I whenever we are trying to do these analysis. So when you see the letter J, kind of from this point forward, what that means is that is the imaginary unit, okay? Now, what's actually super handy about complex numbers is that the imaginary portion of a number cannot combine with the real portion of a number. So when you do things like manipulation of complex numbers, no matter what operation you do on them, you are always going to end up with some real stuff in the resulting number and some imaginary stuff, and the two don't mix together. Maybe that's unfair to say. What you see is that real portion and the imaginary portion of the things that you are operating on, they all kind of contribute into what the result is. So it's not like they don't sort of mix together in the process, but at the end of the day, they are separated back out into a real portion and a complex portion, or excuse me, an imaginary portion. Okay? So what I want to show you is a very common way of representing a complex number, and we do this with what's called the complex plane. The complex plane, all it is that you take the real portion of your complex number and you plot it along the horizontal axis, and then you take the imaginary portion, you plot it along the vertical axis, and when you plot a point in the complex plane, it basically is representing a particular complex number. Okay, so you can already see with this representation that complex numbers are kind of by their nature two-dimensional, right? A real portion and an imaginary portion. So let me show you geometrically what this looks like in this plane. Okay, so let's say that we have a particular real part of this number that I'm going to plot along here. Okay, let me plot it over to there. I'm going to call that A, right? That length right there is A. And then we have another portion of the number that is the imaginary part, and it has a length right up here that I will call B, right? So that's kind of what we're talking about in either of those cases, the length of those two pieces. And if you actually plot where that point would end up from those two pieces, you essentially kind of draw a vertical line like this, draw a horizontal line like this, and wherever that point is, that kind of represents that imaginary number. Now, we often do one little piece that's a little bit better than that, and we often will represent this with a vector. So kind of show the imaginary part and the real part coming together into the total number. So if you're representing a plus bi, that vector right there might represent that a plus bi. Okay? And this is a good place to also mention that there are a couple of handy functions that we use sometimes. One of them is simply RE, or sometimes it's R capital E like this, of a plus bi. What do you think comes out of that function? Okay, these are some simple, just kind of basics. What comes out of that function is just the real part, which is just A, right? What about this function, Im of this imaginary number, a plus bi? What do you think comes out of that? Okay, just B. So anyway, I just take a quick detour and mention that if you want to pick off for a complex number, just pick off either the real portion or the imaginary portion. We have some functions that will do that. And so I wanted to define what those meant right there. Okay, so a plus, well, I meant to do this as JB, and this one here as JB as well. And let me rewrite this one also. I'm trying to keep my notation straight according to how we do it in here. So JB, like this. All right. So this is one totally valid way to represent a complex number. But the other way that we can represent this complex number is with a system that is known as the polar system. Okay? In the polar system, instead of representing it as a real part and as an imaginary part that are sort of separated from one another, what we do instead is we directly identify the length of this vector. Okay? I'm just going to call that length right there C. So we directly identify the length of that vector, and then we secondarily say what angle is that vector at relative to the real axis. Okay? So I'm going to call that right here alpha. Okay? So if you define the length of the vector and you define what the angle is relative to the real axis, you can represent that same number in the form of C, and then we a lot of times use this little symbol of angle, right? C angle alpha. So these are two ways that we can represent a complex number. Now you might say, I still don't see what that has to do with AC. All right, so let me try to go there now. Let's first look at a little bit of geometry here. So we have a couple of conversions that we can do based on the idea that we just built a little right triangle over here, right? We built a little right triangle that has a height of B. It has a run over here of A. And it has a hypotenuse of C. Okay? It also has an angle right here of alpha. So if you're going to want to convert A plus JB to polar notation, what do you think you do? Okay, it's not that difficult. All you do is you look at the Pythagorean theorem on this little triangle, and you say the magnitude or the length of that vector had better be the square root of what? A squared plus b squared, okay? That's going to be the length of the vector. Then you would put the angle symbol, and what's the angle going to be? I know we labeled it alpha there, but we want to express that angle in terms of the AB terms, because if we're converting a rectangular form into a polar form, we want to express it in terms of A and B. So what do we do there? Okay, inverse tangent of B over A. And the only thing I need to kind of warn you about on that is that there is a need to sometimes secondarily look to make sure you're putting your angle in the correct quadrant. Okay? A good example of that is, what if B and A are both negative? Okay, what quadrant would that be in? Okay, that would be in the third quadrant if B and A are both negative, but when you do this calculation, the angle that's probably going to pop out of your calculator is probably not going to indicate third quadrant automatically. So there is a need to come back in and kind of adjust that sometimes manually. Unless some of you might use computer programs, in which case in some computer programs there's a function that's often called atan2. It is essentially a 2-argument arctangent instead of a 1-argument arctangent. And what it does is it looks at the 2 arguments you put in there, looks at the signs, and then it correctly reports which quadrant you're actually in. Okay, so that's kind of a side note there. What if I want to do a conversion from polar to rectangular? What does the geometry say we should do there? Okay. In this case, we know C and we know alpha, and what we'd like to do is sort of calculate what are A and B, right, in terms of C and alpha. So what would the length of side B, like where I have that B length labeled over there, what would that be in terms of alpha and C? Okay, it's just going to be equal to C times the sine of alpha. But what direction is that opposite side over there? Is it along the real direction, or is it along the imaginary direction? Imaginary. So what I'm going to say is we should have J times the sine of alpha. Okay, times what? Times C. Okay, what about the A side? Okay, that one is just going to be equal to C times the cosine of alpha, and we add these two together. And it's often done that you would factor out that factor of C, so you just have C times cosine alpha plus J sine alpha. All right? But these are easy to see just by looking at the geometry of the triangle that we make in that complex plane. Okay? Now, I think I maybe teased you a little bit too soon about telling you, like, what does this have to do with AC electricity? All right, and I've kind of been teasing you along the way too. Let's go ahead and get into that. What does this have to do with AC electricity? Okay, let's take the idea that maybe instead of just plugging in a fixed value for alpha, right, this angle that we have for this little vector right here, what if instead we plugged in a number that was actually time variable, right? That number could actually change with time. And we're not going to do anything super complicated with that. Let's just say that it increases steadily over time, right? That angle just increases steadily over time, okay? Geometrically, what does that do if that angle just keeps on increasing steadily with time? What does this vector do if that alpha angle just keeps on increasing? Okay, it probably, let's say C doesn't change, but alpha does. It's going to trace a circle, right? Because it's going to keep on increasing. At some point, it will have gone around 360 degrees, and then it will keep on going from there, or 2 pi radians if you'd like to think of it that way. Okay. The way we can represent the idea of that thing being time variable so that it just steadily increases is by giving it some value. We call it omega typically, but we give it a value that is multiplied by time, and that allows us to essentially control how fast is this angle increasing over time. Okay? Anyway, what we can look at with this is that if you plug that value into our expression for our polar, our polar expression of that complex number, and then you only look at the real component that comes out of it, okay? What shape is that waveform going to be? Right? I have it written right here. If we plug in omega t in for alpha into this expression right here, and then take only the real component, what does this become? This should be c times the cosine of omega t. And if we plot that, what shape does that look like on this set of axes where I'm plotting the function versus time? Maybe it looks something like this, right? Because that's a cosine function. If I wanted to get even a little bit more specific, where would this point be right here in terms of time? The cosine function, when it goes from 0 up to 2 pi radians, that gets you back to the original place where you started, right? But we have that t in there, so what we need is for t times omega to end up being 2 pi. So what's t got to be to make that happen? Okay, how about 2 pi over omega? Right? That's the t value that you'd have right there. What about down here? Just pi over omega, right? Anyway, but we can kind of see that the shape of this wave is going to be sinusoidal, right? So I'm going to put that note over here, sinusoidal. And when I say that, that's a general term that doesn't mean necessarily sine or cosine. It's just a general idea as to the shape of the wave. Sinusoidal, right? It has the same type of shape as a sine wave, just so happens it's a cosine wave. Okay? So what I want you to kind of see very first here is that what we're doing when we do AC analysis, we are working with rotating complex numbers. And those rotating complex numbers trace a wave on the real axis. Okay? And if you want to see a picture of that, I found this, this picture right here that does a good job of explaining kind of what we are doing here. Okay? What you see with the little vector there, that is a complex number that has a variable angle to it with a constant amplitude or length of it, right? And as the angle changes, the real component traces this wave. Okay? And we're going to take this a little bit further in a little bit, but I want you to actually see kind of graphically what it is about complex numbers that helps us out with respect to AC. Okay? When we have our next lecture, one of the things I'm going to do is show you how what's interesting about this is not really the shape of the wave, because the shape of the wave is going to be relatively the same in our whole circuit if we have a fixed constant frequency, right? We don't necessarily care sort of what the shape of the wave is. We're going to care about things like amplitude, and then another thing that I'm going to show you here right now, right? Amplitude is one of the things we tend to care about. Here's my next question. What would change if instead of plugging in just omega t, we plug in omega t plus some constant angle? I'll call it theta. Okay? What changes about this f of t? Does a lot change or just a little tiny bit? Okay? It's really the same. All you're going to have is c times the cosine of omega t, now omega t plus theta. Right? And so really what we did is we really kind of got the same thing that we got up here with one slight difference. Okay, so I'm going to copy it down here. And then, if I can, I'm going to try to pick off just the wave portion of this and show you one of the things that this does. Okay. So we take that same waveform that we would have had with just omega t, let me change the color, right? And what we've now been able to do by adding that theta, we have shifted, it's called the phase of this wave, by an angle of theta. Okay? And so if we shift that wave by a little bit, this is another factor that matters to us with respect to this circuit analysis. The interesting thing in circuit analysis is not, or at least for steady state AC with one frequency, right? The interesting thing is not that frequency generally. The interesting thing is what happens with amplitudes and what happens with phase angles. And it turns out that complex numbers give us a really handy tool to be able to directly determine those two values without having to get mired in the question of what exactly is going on with the total shape of the wave. Okay, so these are little teasers for what we're going to get to. What I want to get to now is talking about what are the essential properties of a complex number. Okay, so a complex number is a two-dimensional quantity. So here I'm going to go a little bit more mathy with my definition here. Let's say that a complex number, I'm going to denote z, and then we're going to say that that number is two-dimensional, meaning it's composed of a real component and an imaginary component. But even those words are actually not totally necessary to talk about a complex plane, right? You might notice that in my little definition right here, I have not talked yet about real numbers versus imaginary numbers. I'm just saying that if you define a quantity that has two dimensions so that you can have maybe two operands, so that one of these operands is z1 and it is composed of x1 and y1, and then you have z2 composed of x2 and y2, if these two operations, one of them being addition and one of them being multiplication, if they obey this pattern right here, then you have what is defined as a complex set of numbers, right? So these are the essential rules that you have to have in order to have a complex number. All right, well, let's just check them real quick and see whether or not this kind of works for what we think it should, given the fact that we're saying we think a complex number might be defined, you know, just any old complex number zn, we might define this as xn plus j yn, right? Meaning that my first one here, z1, I could say z1 is just equal to x1 plus j y1, and z2, let me make that a little different color so it pops out, and z2 is really just equal to x2 plus j y2. So let's try this out and see what happens if we literally just add the way we think we should, add these two quantities together, right? z1 plus z2, that would be equal to x1 plus j y1 plus x2 plus j y2. What does this equal? Okay, I mentioned before, you really can't combine together a real quantity with this imaginary quantity because it's not the same adding an x to a jy. Those are two different kinds of numbers, right? An imaginary one versus a real one. And so what happens here is this just becomes x1 plus x2 plus j times y1 plus y2. My question is, does that operation obey what I said it had to with respect to addition of complex numbers? In other words, the first number we get by adding the first number in the pair together, right? So that happens right here. Okay, we have the sum of the first pair of numbers. And then we have the sum of the second pair of numbers here, right? And that's what we would have in that second piece. We're just happen to be representing it now in the form of j times that so that it stays distinct from the other portion, right? So I look at that and say it looks like the way we would expect these numbers to work, it looks like they really do work that way with respect to addition. Okay? Now what about with respect to multiplication? Let's check that one out. Okay? With respect to multiplication, what we would have would be x1 plus jy1 multiplied by x2 plus jy2. Now you might remember back from algebra classes, if you have the product of two binomials, okay, how do you do that? Okay, someone says FOIL. Yeah, some people say you FOIL it out, right? What does that mean? First, x1, x2, that'd be the first pair. Then what? Outside, so plus j x1 y2. Then what? Plus j y1 x2. Then what? Plus j squared y1 y2. Now, this brings up a good question. What does it mean to have powers of j? Right? Well, we go back to what we would expect the meaning would be for an imaginary number, right? So if we're saying j is equal to the square root of -1, what happens if we square that? So j squared just ends up being -1. So up here with j squared, I can replace that with -1. Now let me give myself a little more room here. And let's rewrite this now that I'm replacing j squared with -1. And what I will have here is x1, x2, and I'm going to combine that now over here. Because I had that j squared equal to -1, y1, y2 ends up being real. So that is just y1, y2. Over here, I've got j x1, y2, and then j y1, x2. I can factor out that j. And what I'm left with is x1, y2 plus y1, x2. And let's see here. Yes, someone says, shouldn't there be a minus right there? And that was an important thing for me not to forget. Why should there be a minus right there? Because we had that -1 coming from that j squared. Okay? Now, before, well, let's look at this now. Is what I have in the first, or in the kind of the real pair of numbers, is that what I would have expected to have based on my definition of how complex numbers should work? Looks like that's the same thing, right? x1, x2 minus y1, y2. And then down here I have j times x1, y2 plus y1, x2. Up there I had x2, y1. Not different, right? Now, before I leave the idea of powers of j, let's actually extend that out a little bit more. What is j cubed? Would you say j cubed is equal to j squared j? Shouldn't that be what it is? What is j squared? -1, so this should just be minus j. What about j to the fourth? J to the fourth is just going to be equal to j squared, right? Which is -1 times -1, which is just equal to 1. And one of the reasons I kind of chain these up right here and kind of show you what's going on, I want you to see sort of the fundamental cyclic nature of imaginary numbers. Okay? Down at its core, this is why imaginary numbers tend to lead to these periodic functions, right? Things like sines and cosines. It's because these imaginary numbers themselves tend to have this cyclic nature to them. All right, so we've now defined addition and multiplication. What do you think subtraction is? What if I had to take z1 minus z2? Would you think it might be the same thing to say z1 plus negative z2? And what's negative z2? You just negate both pieces, both the real piece and the imaginary piece, right? So subtraction is fairly easy for us to kind of picture what that would be. Division, maybe not so much. So this is something I want to focus in on just a little bit. What if what I want to do is take z1 and divide it by z2? Let me write that out here real quick. What is z1 divided by z2? This would be x1 plus j y1 divided by x2 plus j y2. That looks like that could be a bit of a hassle, right? Why is that? I mean, we basically would have to sort of divide this up and do the first term first with that denominator, then the second term with that denominator. Then we'd have to figure out what does it mean to have a real thing divided by a complex thing. That looks like that could be a little bit of a headache to try to algebra our way out of that situation. So this is a good opportunity for me to bring in another idea that comes up a lot in complex numbers, and that is called a complex conjugate. It makes some operations like this much easier to see how they work. Okay? So, first of all, what do we mean by a complex conjugate? What we basically do is that if z is equal to x plus jy, then z star, that's what we use for a complex conjugate, is equal to the same real component, just x, but now we negate the imaginary component. Okay? Fairly simple thing to do. All you do is you take the same number, but you take the negative of the imaginary component. And this is called the complex conjugate. Let me show you what happens with this problem that I was just working on over here if what we do is multiply numerator and denominator by the complex conjugate of z2. Okay? So basically, what if I came in here and said, what if I multiply this by z2 star over z2 star? Okay? Complex numbers work the same way as real numbers with respect to being able to multiply by a value over itself, right? That doesn't change what the value is. What does that actually look like when I get ready to multiply on this thing over here? Well, in the numerator, I end up with x2 minus j y2 over x2 minus j y2. Okay, now you might say, okay, fine. But what does that do particularly? I guess we can FOIL it out and we can kind of see what this is going to end up doing. Okay, this is going to give us x1, x2, okay, plus j y1 x2 minus j x1 y2, and then we're going to have minus j squared y1 y2. That's in the numerator. What's in the denominator? Okay, in the denominator I will have x2 squared plus j y2 x2 minus j y2 x2 minus j squared y2 y2. All right? So why would we want to do all that? Let's look at these two terms. Here I've got positive j y2 x2 and negative j y2 x2. That means these two should be able to just knock out, right? Now what do I do with my negative j squareds? I can get rid of that and turn this to a positive, right? Can probably do that up here too. J squared is just negative 1, so where I had a negative, I can turn that into a positive. And what does all this become? Okay, I'm going to collect my real things together. This will be x1, x2 plus y1, y2. And then over here, I'm going to have plus j times y1, x2 minus x1, y2. All this is going to be divided by what? Okay, x2 squared plus y2 squared. So if you need to do a division and you have it in rectangular coordinates or rectangular form, right, your complex numbers in rectangular form, this is a way that you can accomplish that. All right, let me show you one other thing that is important, and it will be important with respect to how we represent a lot of our complex numbers and some of the manipulations that we're going to be able to do. And that is a fascinating mathematical theorem that I gave a lot of thought to whether or not I might show you the derivation of this formula. I decided not to, although I might do that in some later presentation or something like that. But this is Euler's formula right here. It says that e raised to the j angle, right? E raised to the j times a number is equal to cosine of that number plus j times the sine of that number. Does that look familiar? Okay. What if I came in here and said, I'm going to multiply both sides of this thing by c? What you see on the right side is the exact expression that I had way up here for my polar method of expressing a complex number. An alternate way to do that, that is totally valid, is with Euler's formula like this. All right? So if you take the coefficient of e raised to this imaginary unit times the number, it is the same thing as that amplitude c multiplied by the cosine of that number plus j times the sine of that number. And what's great about this is that all the rules of exponents that we are accustomed to carry over. So if we need to do manipulations of complex numbers, some of those manipulations might be easier if we have our complex numbers in polar form written according to Euler's formula than other ways that we could think about doing them. Isn't that neat? Okay. Let me show you one of them. Multiplying is a lot easier to do, and therefore division is also a lot easier to do if we have things in polar form. Okay. So let me show you an example of this. Let's say that I have, z1 is equal to, I'll just, pick some variables here. Let's say I have capital A, e to the j alpha. Just pick something here. And then I say z2 is equal to b, e to the j beta. And I want to multiply these two together. What that looks like here, right? z1 times z2. What it looks like is that we would have a, e to the j alpha, b, e to the j beta, not plus, sorry, times. Now, what kind of things can we do with this? Could I collect my e terms? Okay, I probably can, and I can probably collect my a and my b. I could say this is just a times b times what? E. Now, e to some power times e to some other power, what's an exponent rule, like an exponent rule for that operation? You should be able to add together your exponents, right? So that means e now is going to be raised to j times alpha plus beta. So doing a manipulation for multiplication, right? Doing that multiplication in polar form is significantly easier than doing a multiplication using FOIL, right, on your rectangular form. Okay, what do you think a division looks like? What would z1 divided by z2 look like? All it is going to be a over b, e raised to the j alpha minus beta. So that would be multiplication over there. This would be division over here. And both of them end up quite a bit easier if you were in polar form. And you can see that very readily by using Euler's formula. All right. You want to do an example? I do.